the signing. Where, okay. Good. Thank you. Yep. Excuse me, may I ask you then, how many people from here are mathematicians or in mathematics? Please raise their hands. Yes. Yeah. All right. And I suppose that the other are from computer science or from other places. Okay. Yes. Good.
I'll start with the introduction. Happy to have Burghelea today. So this is the first of two talks. The second one will be given, I think, the second week of classes in the spring semester.
Okay, good. Well, I'm happy to have the chance to talk with a large audience in topology and data analysis. And much larger during the time when I was directly involved in teaching at Ohio State. But I'm pleased to have, despite the fact that it's a vacation or almost beginning of vacation for some of you, have the possibility, it's a chance to talk to you about. My talk will be about the dynamics and persistence. And I'm a topologist and sort of analyst. And in the last few years, I was interested in doing topology computer friendly. By this, I mean to revisit a number of concepts and introduce probably another way of discussing classical concepts in topology, but in a way to make them approachable with the computer, which I call it computer friendly. By computer friendly invariants, I mean invariants which can be calculated with arbitrary accuracy by computer implementable algorithm. Arbitrary accuracy that most of the invariants are real number or complex numbers, but the computer can spit out only rational numbers, and that's the reason that this arbitrary is the reason of arbitrary accuracy. But in any case, the lecture today will be mostly some sort of crash course that, if you wanted, in elementary dynamics. And then a little bit of basic Morse theory, and maybe a beginning of Novikov theory, which are sophisticated area of differential topology, and certainly not entirely computer friendly, but my purpose of my talk is to bring them closer to the machine. So about dynamics, let me say a few words about dynamics. Well, actually, dynamics deals with flows on a metrizable space in the most general mathematical form, flows. Well, that means one parameter group of homeomorphism of a topological space, which happens to be metrizable, psi. And obviously, the flows are interesting through the trajectories. So mu x r time x or mu x is a trajectory. It's a subset, if you, of x. Any point dx is in x. And among the trajectory or the elements of dynamics are essential elements of dynamics are the rest points. I will denote it by Carl X. The points or the trajectory remains stationary, so they don't move, the points do not move. Well, a class of trajectory which are visible, which I refer to as instantons, visible trajectory between rest points. So it means trajectory which originate at a point and a rest point. That means when t goes to minus infinity is one particular rest point, and t goes to infinity plus infinity is another rest point, but are visible. In other words, do not lie in, are isolated. Then you can see it experimentally, instantons. And the third class of interesting trajectory are obviously closed trajectory. So they are trajectory for which there exists a t, a capital T, period, so that is gamma of t. Of course, we are not being able to consider all class of dynamics, but I will restrict my attention to a still very large class of dynamics, which appear in many areas of natural science, and particularly in physics. It's called, which I call locally conservative dynamics. For those familiar with the smooth dynamics, I'll say a few words about in a minute. They are exactly given by, let's say, vector fields whose trajectory minimize an action. But otherwise, to describe more precisely locally conservative dynamics, I have to tell you first what I mean by one Chekhov cycle or a topological closed one form. Do not be, let's say, well, inhibited by the long word, one Chekhov cycle, or better say topological closed one form, because that sort of extension in a topological context of what means in differential geometry, differential closed one form, and which is an equivalence class of multi-value maps. So a multi-value maps will be provided by a collection of continuous maps of U alpha is a covering of X, and F alpha minus F beta on the intersection is constant. So this is what I refer by multi-value map. And one cocycle or topological closed one form would be an equivalence class of multi-value map. The equivalence classes means two such multi-value maps are equivalent. If they put it together, remain a multi-value map. In the sense that this condition, it's F alpha minus F beta for the new collection of functions remains constant on the intersection. And the second concept is for topological closed one form. I will say that this one has a Lyapunov for the flow. If any of these functions, F alpha is strictly decreasing on a non-trivial trajectories. And the dynamics which I will consider, well, maybe I'll consider many other dynamics which I will consider are dynamics which are locally conservative. And in mathematics so far in geometry and topology, we restricted our attention to smooth dynamics, and let me tell you a few things about smooth dynamics. The smooth dynamics is provided once I give you a manifold, let's say of finite dimension, can be infinite dimension, but doesn't matter. And in order to simplify the thing, will be closed manifold. A vector field X, smooth vector field. And certainly any vector field will have trajectory, so it will generate a flow. Because it's closed manifold, it's really a flow. It's one parameter group of homeomorphism from minus, for any trajectory being defined from minus infinity to plus infinity. And in this case, we do have the collection of rest points, which consists of a point X where the vector field vanish. And for any such rest point X, you do have the stable and unstable set. What this is, that's a collection of points which lie with a trajectory which arrive into a rest point or originate from a rest point. There is a very precise way to study this sort of thing. For example, the unstable set minus is a collection of points y, so that the trajectory limit when t tends to minus infinity is the point x. Imagine that you do have a manifold, you have a rest point 0 of the vector field, and you have trajectories, the points which lies on various trajectory which depart from the point x, or in other words, a limit of t goes to minus infinity is x. And you do have the stable set consisting of points where this is limit when t goes to plus infinity. Collection of points y is equal to x. For example, well, it's clear if you have a simplest possible vector field in the plane, minus d over dx plus d over dy, will have one dimension of the set of points which are stable on a stable set and unstable set. And clearly the trajectory between 2 points x and y represents the intersection of unstable set from x with a stable set of y, well, divided by translation, because I mean, you can change the point, move with parameter t. So that yes. And in the case of smooth dynamics, you have something else also very interesting. You have a Poincare return map. What is a Poincare return map? Well, imagine that you have a closed trajectory. That will be a submanifold of dimension 1. And if you pick up a point on this type of thing, you do have the normal space to this trajectory. In the tangent space at the manifold, the point x, you might have the normal space. Well, I mentioned the picture is not relevant because here is a rectangle, but that's a subvector space of the tangent space. And well, if you follow with the points nearby, which along the flow, you might go back and to hit against the normal space. And at least near the origin, this map is very well defined, it's smooth, and the linearization of this thing is called the Poincare return map. And in fact, it doesn't matter when you pick up the point, because up to conjugacy, this pair consisting of, let me put here, Poincare return map. For a closed trajectory, gamma consists of a vector space, a normal space. I put here in gamma, although it depends on the point, together with a linear map and gamma, which because it's a flow, that is an isomorphism. It's a linear map. And the pair, vector space, this linear transformation, it's the same up to conjugation. So if you move the point, change by conjugation, up to conjugation. And I should say the dimension of the unstable set, which I have made a picture before, is called the index, Morse index of the rest point. So that's all what you have to know about the dynamics, except that for most of the vector fields, which I should say for a generic class of vector fields, the following beautiful thing happens. Since this space, in this case a manifold, is closed, has compact, there are only finitely many on. All the rest points are hyperbolics. In other words, that simply means that the unstable set and stable set are submanifolds which intersect transversally, and both of them are, let's say, equivalent, diffeomorphic, if you want, or not quite accept the origin, with Euclidean space. The dimension index, respectively, complementary of the index. Number one, so all the rest points are hyperbolic. Number two, instantons, number two, the unstable and the stable manifolds, because they are manifolds for the generic class of vector fields, for most of the vectors, are transversal. Number three, Poincare-Ritter map does not have eigenvalue 1. In other words, Poincare-Ritter map minus the identity, well, up to conjugation is the same thing. Determinant is different from 0. That's very clear that most of the vector fields should have this property. Well, this class of vector fields are referred to Morse-Male vector fields or Morse-Male dynamics. And almost all the vector fields, well, in some, in a sense, it's a generic set of vector fields with respect to any topology CR are likely equal to 2. Yes. And in fact, to be locally conservative, this simply means there exists what the differential geometer and topologists call a differential one form, which is closed. Obviously, this provides you one cocycle because a differentiable form of dimension 1, which is closed locally near each point, is a differentiable of a function. And that's and the function is unique up to an additive constant. So f alpha minus f beta, whatever you do them, have to be constant. So that is about smooth dynamic, and this is about smooth dynamic of Morse-Male vector field, and smooth dynamics which are conservative. So what we call in topology Morse and Morse-Novikov theory is a consideration of such thing. I will tell you the consequence. Well, I forgot to tell you the consequence of being Morse-Male. First consequence was the rest points are hyperbolic and are finitely many because the manifold was constant. The second consequence, in each homotopy class of passes between two rest points, there's only finitely many instanton, finitely many visible trajectory. Well, beforehand, I should say the instanton exists. They are isolated only if the index, Morse index of the first point minus the Morse index of the second point is equal to 1. Okay, and again, all closed trajectories are isolated, and in each homotopy class of closed trajectories are only finitely many. So what that tells you about, it's not important to keep this in mind, except that makes sense, perfect sense to count them, how many they are. And that exactly what a good part of Morse-Novikov theory, and maybe what people outside the topology are interested for dynamics, to count or to detect presence of rest point, presence of instanton, visible trajectory, presence of closed trajectory, and maybe how many there are, if it is the case, to do this sort of thing. So the Morse theory consider only the case of dynamics for which this one cocycle, check cocycle, have only one function. In other words, in different words, the cohomology class of this one cocycles is 0. In this case, the one cocycle can be represented by a multi-value map, but with only one function. And of course, it's a very, very restrictive type of dynamics because it cannot have closed trajectory. If you have only one function, and on each function, along the trajectory, the function should be strictly decreasing in non-trivial trajectory. Of course, you cannot have a closed trajectory. So this is very limited class, but it is very important to tell you the results because this is the first application, conservative vector fields, for which the, let's say, the one cocycle is represented, can be represented by only one function. Of course, can be represented by other sort of multi-value form, but all are the same. Well, I forgot to mention, however, that any of these one cocycle is called the one cocycle because you can associate the cohomology class in dimension 1 with real coefficient. But if you never heard about this, you can simply forget about. Let's say that putting together in these quote-unquote cohomology classes, the one cocycle, you get a representative in cohomology of dimension 1 with real coefficient. So let's tell you a few words about what the Morse theory does. Morse theory. Well, it's not quite the Morse theory which you find in any textbook. It's an immediate consequence of Morse theory which you find in any book, because you will not find in usually book a vector field. But in any case, Morse theory is the way which I formulate it. Consider a manifold Mn, a vector field X, which happens to be Morse-Mail, a generic vector field, and a function f from M to R, which is Lyapunov. But from my point of view, I said you get let's say, a one check cocycle. So that means consider a function f up to an equivalence. Equivalence is two functions, f and g are equivalent if the difference is constant. In other words, if the differential of both functions are the same. Well, that makes sense also for continuous function. You don't have to have a differentiable function. So I would say Morse theory consider this equation, and not quite, I mean, the conclusion which I want to get, not quite f, but I'll put here df, meaning by this one, the equivalence classes, class of function. Well, you see, the point if this is a Morse-Mail vector field, maybe the function is only continuous, and you still can do Morse theory, but however, nearby you can find a really function which you used to know as a so-called Morse function. And in which case, the rest point of the vector field is correspond to the critical points of the function. Well, in any case, let me formulate the basic result of the Morse theory in this language. Here is a theorem 1. Well, maybe I went too fast. So I might say that I can collect and denoted by CK the cardinality of the rest points of Morse index K. And if all the rest points, collection of all rest points is final, of course this would be finite. So one thing, one numerical invariant or basic thing about dynamics is the number CK, which is let's say the number of rest points, cardinality of xk. 2, well, again, in this particular case, the df is equal to, let's say, a cohomology class of df. Of course, the function is, this form, it is exact. Cohomology class is 0. So in this particular case, again, it follows that you have only finitely many instantons. So in other words, makes sense between any critical points x and critical points y, or index of x minus index y have to be 1 if instanton exists. You can count how many instanton are. You can count in more sophisticated way. You can put a sign over them. So in any case, you can count between any two critical points or two rest points, the number of instanton, and get finally a matrix. A matrix, which I call it delta k, which is a matrix of ck cross ck minus 1, a matrix with ck rows and ck minus 1 columns with coefficient in z. But if I fix a field kappa, because I wanted to use homology with coefficient in the kappa, I might regard this with coefficient in kappa, with entry in kappa. So this is a counting instantons matrix. And one relevant thing about this is the number Rk, which is the rank of this matrix, rank of dk. That's second number. That's first number. And of course, I should look at the homology of the manifold M and consider, let's say, the dimension. This is with coefficient in kappa, that's a vector space, and take a dimension of this sort of thing, and I refer to beta k equal dimension of the homology k of M with coefficient in kappa. But of course, I should not put here theorem 1. I should put here theorem 1. Immediately, here it is. Theorem 1. First is ck equals beta k plus rk plus rk minus 1. And second, the collection of numbers ck, beta k, rk, well, depend for any k, depend only on f. Well, a few comments. These rk and ck represent dynamics, number of rest points, and well, essentially information about the instantons. The instanton matrix, I take the rank of the instanton matrix. This represent topology. So the first relation between topology and dynamics. Well, the situation is not very interesting for dynamics because this case of dynamics do not have closed trajectories. And certainly, well, we expect that to consider dynamics which do have closed trajectory, have all the elements. But anyhow, and the second part say that in fact, all the vector fields which admit the same function f as the Lyapunov have exactly the same collection of numbers. Well, first thing, that's a relation between topology and dynamics. And the second tells you, okay, you can get exactly the same result, maybe perturbing the function f if you are able to do it, right? To calculate with another function. But in any case, in any of these cases, this theorem is not computer friendly from my point of view. Even if the manifold M, let's say, can be triangulated as a number beta R, the Betti number can be, let's say, you can design programs to effectively calculate them, but certainly it's very, very hard to locate and with, I mean, in general, the critical points, and it's even harder to get any information of this type about the number Rk, the rank of the instanton counting matrix. However, the purpose of persistence theory, and that is a place where the persistence theory does enter, well, in a very primitive, naive way. Next time you'll see much more sophisticated way. In the next section is that will be to make the full things about Morse theory, to make it computer friendly. In other words, to derive these guys, these numbers, all this collection of numbers, to derive them computer friendly. Well, one thing which is important to do it, you want to know how in the hell we can prove such a result? The idea in the Morse theory, it is the following. Using these rest points, which are in the cardinality ck in dimension k, you get a vector space. This vector space is generated by these rest points of index k. Using this matrix, instanton counting matrix, you can get a linear map from the vector space capital CK maps from xk into the field. At the moment, I'm specifying a fixed field kappa. Doesn't matter which one it is. And then you have use this matrix instanton matrix to provide a linear map, ck to ck minus 1. And well, observe geometrically that it in fact is what the topology is called a chain complex. And number one. And number two, it is this chain complex calculates the same thing as any of the homologous coefficient k you can imagine for the underlying manifold, because all of them are the same since the manifold is a nice space. It in particular calculates the dimension of this vector space. It's the first way to understand the first part. The other one is much more subtle. I mean, to see that in fact, this does not depend on anything but the function f, simply because, in fact, the chain complex you construct obviously depends of if you change the vector field, might change it. But up to not necessarily canonical isomorphism, only the chain complex will remain the same. What is important to say and to explain why is not this invariant not computer friendly, you'll expect that perturbing the function f a little bit, you might get the chain complex might remain isomorphic. No, no way. These numbers are not computer friendly in this way, are not continuous perturbation of the function f among the class of let's say, Lyapunov function does not imply the equality of the number. So if we want to say computer friendly, well, this is much more subtle thing. So now comes the persistence theory, and I will describe you some additional thing which I wanted to mention. So let me erase thing, because I suppose I'll not, I believe or not. Well, I take the liberty at this moment to make a small deviation from the dynamics and what it was Morse theory. This is classical theorem in the Morse theory. Well, I should say the Morse theory is a little more elaborated, more sophisticated. There's something which you can find from any first course in the Morse theory, which I wrote down over there, except point 2 of the theorem. It's much more subtle. Okay, so I will tell you something about the configuration, because my configuration would be trivial. So if I have a topological space Y, I call configuration of Y the set of maps delta from Y to non-negative integers is finite support. That means summation of delta little y, y capital Y, it's finite. So a configuration of a space Y is a collection of points with multiplicity, each of them. It will be, Y will be the complex plane. Yeah, you can regard such a configuration of points with multiplicity as a polynomial, as a monic polynomial. One way to do it, but well, that's not very relevant. On the space of configuration of points of Y, you do have an obvious topology, which I'll refer to as a collision topology. Well, if it would be the case, I might define you precisely a little later, but it's irrelevant because it is very obvious what it means. If you have configuration one which moves to another, that means when the points collide, you will add the multiplicity. And you can invent by yourself the obvious topology, which makes this a nice topological space. You can even, if Y is a metric space, you can put a metric on this space. It's a nice, complete metric space. Okay, and however, well, there's something more. In the case that space Y contains a closed subspace Y0, then on the space of configuration of Y minus Y0, you have a little more subtle topology, which is called bottleneck topology. So if this is a space Y and this is space Y0, bottleneck topology will give less importance to the points as close when they are close to Y0. Okay, you have a configuration of points here. So essentially we'll ignore more and more to the extent that the points get closer and closer to Y0. This is a little more subtle, and I'll give you the definition at the very end of the talk, which I'll have it, or maybe for those who attend the second lecture, if I will be obliged, I'll get to the definition of bottleneck topology. The reason that I involve this sort of thing, it is, I will use actually the configuration which I will use in this talk, at least for the formulating the computer-friendly quality of Morse theory, will be the simplest possible one. The case Y is a real line, or real line minus infinity 0. I mean, the positive number, strictly positive number, can be viewed as all real number except the negative number, negative or 0 number. So, and why is that? Because I wanted to formulate a theorem which will involve the topology on the space of configuration. Well, anyhow, let me go back now and put here this time a second theorem, well, a second fact and theorem. So with the map, let's say, which is Lyapunov for a vector field, or more general, in fact, for any map, which is good enough. It's called the Tay map. I'll tell you in a minute what the Tay map is. For any Tay map, from M, F, R. And in fact, at this time, M does not have to be, for this definition, M does not have to be a manifold. That will be very important in a few minutes. Not necessarily a manifold, but a nice space. For example, any underlying space of a simplicial complex. Or if you want a manifold with corners or whatever. But I suppose that is what we call in topology compact INR. But you don't have to know what this compact INR means. You should think about, let's say, as a basic example, a space which is homeomorphic to the finite simplicial complex. Okay, well, compact space which have a triangulation of a simplicial complex, whatever. One can produce for a field, a fixed field kappa, we can produce a collection of configuration, delta R. Let's say, put here df, which is configuration from R to configuration on the points on real line with multiplicity. And the configuration gamma df R for 0 infinity in Z. Here it is 0, here it is infinity. So points with multiplicity. And 1 and 2, blah, blah, blah. Incidentally, such a configuration is simply given by a collection of numbers with multiplicity. So it's something which is computable, makes sense. It's a geometric, interpreted a geometric object if you want, but it's something very computational, reasonable collection of numbers with multiplicity, finite collection of numbers with multiplicity. And the second is a positive number with multiplicity. Well, here is theorem 2. The number beta r is a summation of delta df r of t. The number rank r, it is summation of gamma df r of t. And the number cr are the number beta r plus r plus r minus 1. As you can see, to the extent that this configuration are computer friendly, everything is computer friendly.
Just a question. So, did you say that the first configuration maps into the
first configuration is a collection of real numbers with multiplicity. The second configuration is a collection of strictly positive number with multiplicity. The second configuration, let's say algebraic cardinality or the sum of gamma f r, it is exactly the number r. The other first one is exactly the, yes, beta r. And therefore, you can find CR, the number of rest points of index K, as a sum of the cardinality, algebraic cardinality of this configuration, plus the algebraic cardinality of this configuration, plus the algebraic cardinality of the same configuration with r minus 1. And the second one, 2, it is the assignment T map d the f r, respectively f from gamma df r are continuous. That from uniform convergence topology of the space of maps, well, they stated to the T maps, if you wanted to the configuration with collision topology. And here from these maps, from the space of T maps, equipped with a convergence uniform topology, to the configuration of the second type, but with bottleneck topology. Well, of course, this suggests you that delta, this configuration are computer friendly, suggests you in some sense, in the sense that, well, if I succeed to calculate this configuration for some nice class of maps, I can calculate at least this number for all other because of this continuity property. Well, in any case, I will describe you a little bit more about this matter, because here it is what the persistent theory was entered. But I will, yes, and I will explain this in a minute. You see, okay, you might jump at the moment and say, but you say that this number RR and CR do not depend continuously of F. It's a little bit of contradiction here, continuously on F or net. No, you'll see in a minute why, how this configuration are given in terms of barcodes. And well, yes. So first of all, no, next, let me explain the relation with persistence. In fact, the relation with persistence can be made only in this case of a Morse theory, namely in the case that homology class of the topological closed form is trivial, is 0, or in other words, we have the multi-value map represented by only one map, F. And well, I forgot to tell you what a TAME means. TAME is something very, very simple. It is a continuous map from this topological space to this one. This is supposed to be a nice space, a compact INR. And the first condition to be obtained is the inverse image. The level of any of them remain at ANR. ANR have very beautiful property that if they are compact, the homology with coefficient in any field is finite dimensional. And in fact, it's finite the group with coefficient to be an integer as well. First condition. The second condition is the levels f-1 of t change homology only at finally many t, or a discrete collection of t. Well, since M is supposed to be compact at finally many t. So that this means a tape map. Of course, you'll see that this is hardly insufficient for more general case where we wanted to study dynamics. It's hardly sufficient for this case. All right, so then let me say at the moment, what is, first of all, this theorem does not make any substance because I didn't tell you what this guy are. I only suggested to you are computer friendly. But I suppose that some of you are familiar, but if you are not familiar, it doesn't matter because I'll get a completely different perspective on this persistence next lecture. And I suppose that you are familiar with so-called the zigzag persistence, or what I'm calling level persistence for a continuous map or a tame map from a space X to R. So that for, if you fix the field kappa and a number R equals 0, 1, 2, blah, 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 and this is a compact, nice space, compact INR, for any F, you have a collection of, 4 collection of barcodes, closed barcodes, which consist of closed intervals A, B with multiplicity, A smaller or equal to B. And the open barcodes, open R, which are intervals alpha, beta, alpha strictly smaller than beta, and closed open barcodes, which are alpha, no, let's say A beta, A strictly smaller. And you might have also open closed barcode, but that's, yes. Open closed barcodes can be closed open barcodes for the function minus f, so I'll not indicate them. So any of them can be represented, let's say, in the plane R2 with a main diagonal. The barcodes can be represented at points with multiplicity above the diagonal, including the diagonal. Open barcodes, alpha smaller than beta, can be represented at the points beta comma alpha below the diagonal. And I'm telling you what? Well, no, I want to tell you that for such a map, you can also provide a slightly more sophisticated, and for such a map, slightly more sophisticated configuration. It's not more sophisticated, actually less sophisticated by, let's say, more obvious configuration. Delta F can depend on F, not of F up to an additive constant, from R2, R into Z. And the configuration gamma F R from R2 plus, that means the points A, B, A, 60 smaller B in Z. Defined in the following way, not entirely obvious, for points of coordinates AB above or on diagonal I'm taking exactly these closed barcodes with a value of the configuration exactly the multiplicity. Better say that the support of delta FR is exactly the same intersected with R2 plus, no, so R2 A is only equal to B. It's exactly the same as a collection of barcodes, see, with support as the points are exactly the same as the points represented by barcodes. The value of delta FR is exactly the multiplicity of barcode. And support of delta FR intersected with AB, A larger than B, is exactly the same after, let's say, permutation of the ends, because the barcodes, open barcodes, but of dimension R minus 1. So we have closed barcodes, and here open barcodes. So they represent barcodes with multiplicity above or on the diagonal, barcodes with multiplicity below diagonal, but of course, since A is larger than B, as an interval should be B alpha. But you see, are not the same. And that explains you the sort of continuity. When you perturb the function f, you can move from R barcodes, closed barcode, to an open barcode, but not an open barcode in dimension R, of degree R, but of degree R minus 1. Okay, well, in any case, well, the picture is, representation is pretty much the same for gamma FR from R2 plus, then is alpha smaller or equal to beta into Z plus, which involve the closed open barcodes. So these are other configurations. In the plane, respectively above the main diagonal plane. Well, what's the relation between this one and that one? Well, first of all, I should add that if you are familiar with persistence theory, with level persistence, zigzag persistence, or whatever you want to call them, the barcode has ends always critical value of the map F. If the map F is only continuous, what means critical value is simply the value when the homology of the level change. Certainly, for the Morse function, the critical value in the calculus way are exactly the same as critical value in this topological sense that happens for any field kappa. Okay. All right, so there is another observation. If you change the function f, adding a constant, you shift the barcode. However, the length of barcode, b minus a, does not shift. So my formula for delta df of t is a sum of delta f of a b minus a equal to t. This sum is finite. Put here r, put here r. And the same thing of gamma df r of t equals sum b minus a equal to t of gamma f r a b. And in view of the observation I mentioned, doesn't matter if you calculate this with f or you calculate this for f plus the constant. The outcome will be the same, because the difference remain of this sort of thing remain the same. So you know a bit about this configuration in T. There are configuration at the points of the real number, which happens to be the difference between two critical values. So it's quite, yes. So from this sort of thing, you can get the feeling, or this is a collection, the immediate connection with the persistence theory. Okay. Well, since most of you have, if you read about the persistence theory, knows that if you have a simplicial complex as a space X and you have a simplicial map, there is a very precise algorithm to calculate the barcodes. You can find either in work of Gunnar Carlson and company, or even in the work of Tamar Day and myself. And you can find algorithm. And therefore, you have algorithms for calculating delta df and gamma df. And therefore, you have algorithms for calculating the number CR, capital RR, and beta R using this relation. So everything becomes, well, for, let's say, a simplicial complex and simplicial map. Oh, because of item 2. Well, foul being situation give you more precise statement of this one. You know what accuracy you have to do. You can replace a T map by one, which is in the case of simplicial complex, which is simplicial up to possible finite, let's say, division of this one, which will give you the chance to calculate with arbitrary accuracy this thing. So finally, we ended up in the case of Moore theory with a form which I can, well, at least me, who is not an expert in algorithms and the complexity of algorithms, and think about algorithms as something which is, in principle, you can put it, I don't, in a computer, but I don't know how long it will take it, if it's a good algorithm or not. Theoretically, is computable with arbitrary accuracy because of item 2 of the theorem 2. Well, this is the very good situation in case of Moore theory, but it's not so interesting because very few interesting dynamics are modeled by, let's say, by a topological closed one form with cohomology class 0. In general, they are cohomology class different from 0. In fact, in physics, you do have an action, but action by in a very, very few circumstances happens to be the differentiable given by, let's say, a function, an energy, or whatever you want to say. Otherwise, it would be a closed one form. So what's the next? I do have a few minutes. I'll prepare you for the second lecture. Well, the second lecture will be about the substitute for persistence theory in that case. I should say that the intermediate step here was construction of the configuration delta F, which is the configuration of points in the plane or in the plane above the diagonal. And then from this configuration, get the configuration delta df, which depends on the form. Well, this doesn't work entirely, I said. You can provide, in the case of arbitrary closed one form, by all sorts of manipulation, as you see next time, such thing like a map, delta F, for some F associated with the form, but will not be, this form will not be, by no means will be not a configuration. It will be simply a function with not zero part. However, ultimately, as I will try to explain what happened in the case, in the most general case in a minute. But in the general case, which is a topic of Novikov theory, in the case that you have a smooth dynamics together with smooth closed differentiable one form. Well, in any case, or in more general case, I forgot to say you, whatever I told you here about smooth manifold with a smooth dynamics, which is locally conservative, works with slightly more modification for an arbitrary flow for which the rest points are isolated and for which you have also instantons, which are finitely many visible instanton, which has finitely many. And well, the full theory works for closed trajectory and does not have to be, in any case, on a manifold. Not this, the flow should not be described by a function or whatever, but let's say, well, by a Lyapunov function, yes, but the flow is Lyapunov. So it extends considerably. Generality or standard Morse theory can be described, or it is described in almost any textbook. Okay, what happens if you have a space, let's continue denoted by M, and you have a topology, a closed one form, let's say a smooth one form in the case of smooth dynamics, omega, well, let me put here, omega 1M, with d omega equal to 0, which represent the cohomology class C, omega H1 of R. Let's tell you a few definitions of algebraic topology of this pair, because I expect that in the case when I will have a smooth dynamics, which is the Lyapunov closed one form, and which will have also instantaneous closed trajectory, to be able to say something similar, but and I have to make some modification, well, to complicate a little bit the algebraic topology associated with this one. So first of all, let's suppose that I have C, cohomology class. The moment I became a little more expert, I mean, the people should not only be more algebraic topology, but very elementary algebraic topology, H1 of M with coefficient in R. You know that this is exactly the same thing as harm from H1 of MZ into R. And once you do have such a cohomology class, you have a group gamma is actually image of C, which lies in R. And if this M is compact, that would be the case, this is finite generator, and that will be finite generator, so it will be finite generator, so this has to be isomorphic with ZK. So we have a subgroup isomorphic ZK inside of R. Well, of course, if this cohomology class is 0, that's a 0 group. It's a more cohomologic. If this is Z1, that's Z lies inside R as a lattice. But if K is larger or equal to 2, that's very bad. This is always everywhere dense. So that little observation, everywhere dense. Okay, that makes the situation complicated from the point of view of persistence, considerably more complicated to try to mimate what the persistence theory does for such a situation. But in any case, we always get a principal covering, a gamma principal covering of M. This simply means another space M tilde on which gamma acts freely, such M is M tilde divided by gamma. As a consequence of this thing, the homology in dimension K of M tilde was coefficient in kappa. Well, even if M was compact, or even compact INR, that's not a finite dimensional vector space, unless K equal to this, not kappa, this is kappa, not K. Kappa, a field kappa. Unless K is equal to 1, no, is K equal to 0, this thing is infinite dimensional vector space over the field kappa. However, it is so-called a group ring. It's a module of a group ring Z gamma, which happens to be, let me put kappa gamma, which happens to be the Laurent polynomial in K variable isomorphic. Dk T1 minus 1, dk minus 1. Still a very reasonable ring. However, does not, well, it's finitely generated module over this thing. Well, the key observation of Novikov, or key idea of Novikov, is it can extend the theory, but with doing a little bit more complicated homology or complicated algebraic topology. Namely, one can construct a completion of this group ring to a field. For example, if k as it happens to be 1, this will be the ring of Laurent polynomial associated with kappa, and this field will be very simple in that particular case. Otherwise, well, yes, it's cannot say too much about. And otherwise, it will be Laurent power theory. Here will be Laurent polynomial. If k is equal to 1, otherwise it will be Laurent power theory. That's a very simple situation. But otherwise, it is a field. And if it is a field, you can look at the homology of M field, tensor this field over the ring, because it's a module over kappa gamma. Everything is over is a commutative ring. It doesn't matter left, right, is irrelevant. And that will be a vector space over this field. And that will refer to as a Novikov homology. And the dimension of this is finite generator, so it will be a finite dimension vector space over this infinite field, very large field. And the dimension of this one will be referred to HNR. See, which is, of course, an integer, finite integer, would be Novikov Betti number. So what's the outcome in the general situation? In the general situation, if you start with smooth dynamics, or maybe more general dynamics, as I mentioned, again, the critical points, because this Morse-Male vector field are finding many, so the numbers CK are very well defined. You try to count to get an analog of the instanton counting matrix. Well, it's not so easy, because instanton between two crest points can be infinitely many, although they are discrete, and each homotopy class is defined. However, you can obtain a matrix whose coefficient is this Novikov field. That's the next observation of Novikov. So, and therefore, a matrix, CR by CR minus 1 matrix whose coefficient in the field has a rank. So the number in all cases, the number CR are well defined, the number RR are well defined, and the number beta R, well, maybe defined, it's exactly the number which I have described it as a Novikov-Betti number. Theorem 1 remains valid exactly with this thing in this context, but with the observation that the Betti number should be replaced by Novikov-Betti number. Okay, this is from the very beginning highly non-computer friendly, because even the field, being a very infinite field, there is practically no way to put the hands on it, let's say, in any existing algorithm in the algebra so far to my knowledge. And therefore, to calculate the Novikov-Betti number, these are far from being, well, a priori computer friendly. However, what I will discuss next time, completely independent from this discussion here, I will discuss this sort of configuration. Delta, where here will be an arbitrary closed one form omega, gamma, which will be closed in omega form omega, which I will show they are computer friendly. So that's a general story of the lecture today. And next time we'll provide this sort of thing. And the description of this configuration, an intermediate way to reach this configuration is alternative treatment of the level persistence in the case that the map is far from being traditionally, let's say, a map or There is no way to use, let's say, quiver representation, decomposition, decomposible representation, nothing like that, because everything and all the vector space which appear would be infinite dimensional till the very, very end when you get to finite numbers. So that's the story for today. One thing, the lecture for today will be posted on my website. I do have, let's say, slides, reasonably well-organized slides. Not like my writing, but I never like it to use a...
Put it on the seminar website too if you want.
Okay, yes, I'll put them. Yes, or I'll give it to you in the next few days, yes. Yeah.
Questions?
Yes.
Do you think it would be possible using the tools of algebraic geometry to be able to calculate or approximate Novikov-Bethe numbers?
Oh yes, of course. That is from this theory that Novikov-Bethe numbers, I forgot to say, becomes computer friendly. And in fact, the approximation is not a big deal because they are integer numbers. So you don't have to go very far to approximate that. You a priori get some rational numbers, but well, these rational numbers have to be integer numbers. So that is okay. Well, I forgot to say, one of the reasons was exactly this one. So how to get away of computer-friendly approach of Novikov-Bethe number, which are of relevance for dynamics.
I mean, if it's an integer, it's fine, but what if it's a persistent Bethe number, Novikov-Bethe number? That might be more.
I'm not sure what is persistent Novikov-Bethe number because
values not integers. It's always integer.
I'm sorry.
Can be modified to be non-integer.
Not integer. No. Well, there is a. The configuration we propose are not integer, are real numbers actually. Are real numbers.
That's why it's...
The cardinality, the sum of multiplicity of this sort of thing becomes a Novikov-Bethe number, which by definition is dimension of a vector space over a field. But this is, well, if you look in on the net, you'll find article of mine, refinement of the homology of Novikov homology. So refinement of Bethe number is exactly this configuration with the sum of multiplicity is the Bethe number. And but these are real numbers with multiplicity, sum of the multiplicity. So that's it. And in fact, this thing is much more sophisticated, saying the full homology as a vector space, including the Novikov homology, has to be decomposed as in the complex analysis or complex geometry, image-Hall decomposition in HPQ types, this sort of thing, and the subspaces indexed by the support of this configuration. Well, the theory is certainly something which I'm still thinking about it, and it's attractive. But there is the most interesting thing which I would like to do it is, well, I like other people to do it because I'm not in a situation to convert this algorithm in effective algorithms. By effective, I mean just to do some example. Well, incidentally, I have not put any references. There are 3 references of this sort of thing. One is on my book, New Topological Invariance, and an alternative to Marsh-Novikov theory, which consider only in a different language the case of when a cohomology class is integral cohomology class or rather rational cohomology class, which means they reduce geometrically to the maps, not real value map, under value maps. But reduction is not any, but it's very simple. So all the details for this type of thing, including algorithms and this sort of thing, in this particular case are done.
Any more questions? Let's thank that.